Hey there, and welcome to this next lesson on higher mathematics algebra. I've mentioned a few times now about simultaneous equations. This is when we've got uh, an equation of two variables, and we've seen before you can't really solve that by itself, but so we need another piece of information, and that other piece of information can be a second equation. So we have two equations of two variables. That is now something we can solve, and so we're going to look into how that works. So here are our four sections that we're going to be looking at today in today's lesson. So first of all, let's just go over that graphical interpretation of simultaneous equations first in a bit more detail. Because it's good to help understand, what's actually going on. Then we'll look at simultaneous linear equations. So well, we've just got two linear equations, which is the basic case, which is what we'll encounter quite often on higher level mathematics. It's quite likely you'll encounter simultaneous non-linear equations. But when I say that, I mean it's going to be a linear equation with a non-linear equation. You won't really get two non-linear equations, and because we always have that linear equation, you'll find it's not actually that bad, and we can always use that to find the solution relatively easy. We'll see how that works. And then finally, forming equations. So this is when we're given something more in words, like just some information, and we need to be able to extract equations from it and then solve them simultaneously. So this is something that often pairs uh, with simultaneous equation problems, and it's very important to be able to do because this is what we actually do in the real world. You have real world, information, and we want to define what our unknowns are, and then produce equations from those unknowns, and then we can solve those equations. Then that's when all our algebra skills uh, come into play, but they're not any use if we don't know how to form equations in the first place. So that's what we're going to be looking at there as part of this lesson. So first of all, the graphical interpretation. So we've seen before what that is in terms of more when it was like two linear equations. So here I've got a quadratic equation. Um, Remember what that represents is it's basically all the points that are solutions to that equation. So you see all these points I've generated here. You could try plugging in those x and y values into that equation. You find it won't come out to the correct value. It won't be equal. But you take these points along the lines and you substitute that into the equation, you'll find both sides will be equal. And so that's what this line represents. It's all infinite number of points that would be a solution to this equation. And if we had a second equation like this, a linear one, and that line represents all the solutions to that equation, these 2 points are then going to be the solutions to both of these equations simultaneously. It's the 2 points where both of these equations are true simultaneously. And so we've seen before you could, so in this case, there's actually two solutions as opposed to one. Theoretically, you could have an infinite number of solutions, depending on what functions or equations you're looking at. You only ever see cases when there's either one or two solutions. And so you see here, we could read this off graphically if we wanted to. But we want to see, okay, these two as like a system of two equations, how would we solve this mathematically if we wanted a precise answer? So let's quickly go over the different combinations you could get first of all. So you've got the basic case, which is two linear equations. We're about to look at that in a second, where you're just going to get one solution because it's two straight lines, isn't it? So you think that's the thing. It's good to think about things graphically because when you see two straight lines, it could only possibly intersect at one point. So you see, you only get one solution. Whereas a quadratic like this, you could get two solutions, or you could potentially get one if the line just touches the curve and then goes off. It's theoretically possible to get no solutions as well. If you had something like a circle, again, if it just touched the circle, you'd get one solution, but generally you'll get something like this where there's two solutions because again, it's going to intersect the graphs twice, so you can already tell there's going to be two solutions. So these are graphs you're very familiar with. Other graphs you're maybe not familiar with is something like this, like an ellipse, which is like a circle that's been squashed or stretched slightly. You wouldn't be expected to be so familiar with this graph, but we do get scenarios like this where we have to solve these equations simultaneously. But it's not too bad because we can solve it very much in the same way how when we've got a quadratic or circle, and we'll see how that works. Also with something like this, where you see the x squared we've essentially got like an x squared minus y squared, and it produces this weird shape. It's what's known as a hyperbola. And again, you can often get two solutions like this. Again, this is a graph that you don't have to be that familiar with. You wouldn't really be tested on this, but we do get equations like this that we would be still expected to solve simultaneously, but it's not as bad as it might first seem. So uh, those are the different kinds of cases we'll get, and you see where you either get one or two solutions. We're looking at first linear equations. So two linear equations, we know there's only really one solution to that. And we have two methods that we use. First one called the elimination method. So say if we have two linear equations like this, and you see we don't have it really in that form y equals mx plus c, although we could. That's what we often use for graphs. Simultaneous equations, we often get it into this form where we line up our x terms, y terms, constant terms, uh, like this, the two equations. And you'll see why we do that in a second. Now, the elimination method, the secret is, right there on the tin, really. We want to eliminate one of the variables. The problem is here, we've got two variables, and we can't solve that equation for a specific value. You essentially get infinite values. But we can use one equation, like if we're trying to solve this, try and find out where they are simultaneously, we can essentially use one equation to eliminate a variable in the other equation that then produces an equation that we can then solve. So let me show an example of how that works. So say with this here, what we want to do is look at the coefficients of our x's, look at the coefficients of our y's, and see how we can get them to match. So I would go to match the x's, and what I could do, I could multiply that second equation through by 3. And you see that 2x will become a 6x. And obviously, to keep the equation in balance, I have to multiply everything through by 3. But you see, the main thing is that those two x terms now match. And so now we can do something that is akin to like a long arithmetic, like what we saw with long addition, log subtraction back in lesson 1. We line up our numbers, like the place values, and we can then subtract down each place value and, carry out 1 or whatever, things like that. And it's kind of a similar thing here, because we've lined up our constants. We can just constant the y's, the x's. We can essentially subtract down each column, and we'll get this: 3y minus 18y gets minus 15y. 12 minus 42 gets minus 30, and then obviously the 6x minus 6x just cancels out to 0. Because what we're really doing here is, okay, basically we've got two equations. Equation has a left-hand side and a right-hand side, and they're equal. So what we're doing is we're doing the left-hand side of the first equation minus the left-hand side of the second equation is equal to the right-hand side of the first equation minus the right-hand side of the left-hand of the second equation, which makes sense. If the left-hand side is equal to the right-hand side, then the differences between the left-hand side and the right-hand side are going to be equal. So you might want to take a second to think about that, if that check that makes sense. But that's essentially what we're doing when we subtract down the columns like this. So we get this, and you see this is a very simple equation, of y. We can divide by minus 15, we get y equals 2. And that's the tricky part, because now we can just go back to the original, or one of the original equations we had, like this one. We can substitute in our value for y, and now we've got an equation for just x that we can solve and get x equals 1. And so when we're substituting, well, not substituting, when we're eliminating variables like this using one equation, like you're using one equation to eliminate a variable in the other, you're essentially going to be left with these values, which are going to correspond to the values such that both of them are true, which is precisely what we're trying to find. The values where they're both true simultaneously, hence, simultaneous equations. And we know graphically this would correspond to their intersection. So their intersection would be essentially at this coordinate. So that's like a basic method of how we would solve simultaneous equations. Let's look at one that's a bit more complicated. So same kind of method where we need to get the coefficients to line up, but here we've got some trickier numbers, because you can't just multiply 14 by something to get to 21. You can't multiply 9 by something to get to 11. So we need to multiply both equations through by something, but we want to pick the easiest one we can, the one that will make the smallest make the coefficients as small as possible, especially because we've got some big numbers on the right there. We don't want them getting too big. Um, so what can we do there? What we can do is we want to find a number that we could multiply, say, the first equation through by, and the second one through by, such that these coefficients are going to match. So we need a number, like say if we're looking at the x term there, we need a number that's going to be both a multiple of 14 and 21, but we want the smallest one possible. Well, that is basically the lowest common multiple, isn't it? And we know how to do that. If you don't, you might want to recap the lesson on prime numbers. So we see the lowest common multiple is 42. 14 times 3 and 21 times 2. So we could, multiply through those equations like that. Uh, we wouldn't really want to get the y variables to match because that would involve multiplying through by 11 and 9. We can't really do any better than that, and those are much bigger numbers. So this one is much nicer, just 3 and 2. And if we do that, we get these two equations here. So the x match this time. So now we can do subtraction in the same way we did before. We get 5y is equal to 19, so y is equal to 19 over 5. And now we can add that, substitute that value of y back into any of our equations to then solve the corresponding value of x. So I've gone back to the original equation we had of 14x plus 9y equals 95. You can substitute into any equation and it'll work because all the equations are going to correspond to that solution. Both the equations, um, the graphs they intersect at that point, don't they? And any scaling we've done like this, where we're multiplying through the equations to produce these new equations, they're essentially the same equation, and so it's fine. You could plug back into anything. It's kind of like with a fraction. Say if we had 2/3 and we scale it up, maybe I times the top and bottom by 5, and I get 10/15. The numbers are different, but it's still the same fraction, isn't it? The value of it is still the same. And it's kind of like the same thing here. If I multiply through an equation by a number, it's still essentially like the same equation. So yeah, you can substitute back into anything. And then we just need to rearrange this. So here we've got a bit of fractions going on. You need to know how to do your arithmetic there to get the denominators the same. And then we're dividing by 14. One like this, you might even have a calculator available for because it's a bit trickier numbers. So that's the tricky part is solving for that first variable. Once you've done that, you can always just substitute back in for the other one into whatever equation looks easiest. We have another method called the substitution method, which for linear equations sometimes has uses, but you'll see this has a lot more use when it comes to looking at the non-linear ones. For those more difficult problems, you really need to know how to do substitution method because often that's the only method we might have. So the only one that will work. So what it is it's when you've got like an equation like this, where like that top one, where one unknown is the subject. So here we've got x is the subject. X equals an expression of y. And if you've got something in that form already, then substitution method can be good. Or if you're asked to work something out using the substitution method, you then need to get it into that form first. So you make one of them the subject, whichever one works out, easiest really. And then what we can do is we can substitute that into the other equation. So 3x plus 4y, if I know x is equal to 2y plus 5, so I've got x as an expression of y, I could take that little expression of y and stick that into the other equation wherever there's an x. So 3 times x, I instead now have 3 times 2y plus 5. And then the rest of it is plus 4y equals 20. So that's all the same. So you see what I've done there? I've now produced an equation with just one variable, and that's the key. So it's kind of similar to the elimination method. Both of them are the same in the sense that you need to produce an equation of only one variable that will correspond to our solution. And this is one way of doing it. Substitution. So now we just need to expand this out, collect together our like terms. We'll get this 10y plus 15 equals 20, and we can solve that to get y equals a half. And when using the substitution method, that equation that you have where, like say here in this case where x is the subject, you always want to substitute back into that one. Like that's the easiest one to work because you've already got x explicitly as the subject. So I just put in my value of y and that will just, generate my value of x that I need. So 2 times a half plus 5 gets us 6. So there we go. That's our Solutions, that's our coordinate where the graphs intersect, however you want to view it. So that's solving linear equations. And we've seen our two methods there. And now let's look at simultaneous nonlinear equations. So the different cases we can come across. So here's the first one where we have, say, a linear equation and a quadratic. Now, a quadratic, when your nonlinear equation is a quadratic, you could still do this using the elimination method. So we could do one, subtract the other, and you see the y variables could cancel out and would produce a quadratic of x. But I'm going to just use the substitution method because generally speaking, yeah, with nonlinear equations, that most of them you will need to use substitution methods. So let's get some more practice on that. So say if I rearrange this to make y the subject, so I've just subtracted x from both sides. Okay, so I've got y equals this linear expression of x, but I've also got y is equal to this quadratic expression of x. Well, I can just set those two expressions of x equal to then. If they're both equal to y, then they're equal to one another. And I rearrange this by, adding x and subtracting 2 from both sides. So that right-hand side now just goes to 0. And I've got this in a quadratic in the form that we always want to get it into. A quadratic equals 0. We can now just solve this in the usual way. I've chosen to complete the square here. You can't really factorize. You'd have to complete the square, or you could use the quadratic formula. And you solve, and I get this. So not such a nice value for this one. It's like a surd form, a plus or minus, surd form. Now for y, again, as always, it's always easiest to just substitute back into that one where y is already the subject. So it makes life easier for us. So when I do that, I do 2 minus this value of x. Now I've used this compact, plus or minus form. And you see, okay, so I'm doing 2 minus x now. And let's talk about the plus and minus form for a second. So what that is basically doing is it's showing two expressions in one. So it saves us time. Like when you've got two very similar expressions, like for x, we've got minus 3 over 2 plus root 21 over 2. And we've got minus 3 over 2 minus root 21 over 2. And rather than writing all that out, we can just do plus or minus. But here, when I'm doing then the y, you've got to be very careful because I'm subtracting the x. So I'm negating that. The plus minus becomes a minus plus because plus times by minus gets minus, and the minus times minus gets plus. So you see how the plus is going to turn into a minus and the minus turns into a plus. So I've now got this compact form for my essentially 4 solutions, 2 for x and 2 for y, and you just then got to make sure you read them off correctly. So if I'm reading across the top, I get the plus on the x and then minus on the y, and then the minus on the x and then the plus on the y. You've got to make sure you pair up your solutions correctly. If you're not so comfortable with that plus or minus plus form, then just write out the specific value. So you'll get 2 solutions for x, and then you could substitute each one individually to find the corresponding y's, and make sure if I substitute in this one and get this solution, then them two go as a pair. And then I get substitute in this other value of x and get another solution, those two go as a pair. So make sure you pair them up correctly. So let's take a look at another one. So this one is kind of like a circle, but it's actually an ellipse if you remember from earlier, because the x squared and the y squared are being multiplied by different numbers. So how do we solve that? This is an example of one where we really do need to use substitution now. Elimination is just not going to work. And I've already got the y as the subject for our linear equation. So it's a very similar story where we've got y as an expression of x, 3x minus 1. So what I can do is I can take that and substitute into the other one. So where there was a y before, or a y squared, I now put 3x minus 1 squared. And so now you see here, it might be quite a complicated equation, but it's essentially just an equation of x. A quadratic equation, in fact, because you can see you're only going to have x squared terms. So first of all, I'll do that 3x minus 1 squared. I've expanded that out. And now I have to multiply that through by 2 and then collect together my like terms. I'll essentially get this. Now I've got some big coefficients there. You see there's a common factor we can cancel out, a common factor of 3. So now we've got this quadratic, um, and we need to solve that in, again, any way that works best for you. And you'll get this solution here. So we've got our three methods. I'm not sure if can this one be factorized? So perhaps or perhaps not. I'm not sure actually off the top of my head. But well, I've got that solution there. And you see this time, we don't have a square root part. We've just got essentially the addition of subtraction of two fractions. So we could just work those out. We get 11 over 7 or minus 1 if we do, the plus and minus there. So that plus or minus notation is normally when you've got things in surd form. But if you get something like this, you might as well just work out the actual fraction or integer value that you're going to get. And then substitute each of those individually into, again, the linear equation that we've already got y as the subject. So y equals 26 over 7 or y is equal to minus 4. So again, make sure you pair those up correctly. So let me show you a quick example here of if you don't correctly put them together. So here's with them put together correctly. 11 over 7 goes with 26 over 7, and the minus 1 goes with the minus 4. And you see that corresponds to the two solutions. If I plot these two graphs, if I paired them up incorrectly, you'd actually get these two coordinates. And you see, not only are they not at the intersections, they're not even on any of the graphs at all. So yeah, really make sure you pair them up correctly. That's important. So let's look at another example. So one like this, which is that non-linear one we have, is essentially going to be like an algebraic fraction. It's kind of in disguise, like it's been rearranged. Like you might not be able to recognize that as an algebraic fraction. It's a complicated one because you've got that xy term. But like I said, you're only ever going to have one non-linear equation. You've got then the linear one at the top, and we always know that can be put. We can make one of them the subject. In this case, I make x the subject rather than dividing by 4 to get y as the subject. So I've got this. I've got x now as an equation, like in terms of y, and it's just same as usual. I can substitute that into the other equation. Wherever I see an x, I'll put 2 minus 4y instead, and then just got to expand it all out. Let's collect together like terms, and you see, okay, I've got this equation of y, quadratic equation of y. So you need to be versatile. Sometimes we get sometimes people get used to always eliminating the y to then produce an equation of x, but sometimes you want to eliminate, it's easier actually to eliminate the x and get an equation of y instead, like this. So, but we can use all the same methods. So we factorize this, and so yeah. Oh no, sorry, not factorize. I realized because I've moved the constant over to the other side. No, I've actually completed the square here. So, because completing the square is a good option here because the coefficient of the y squared is 1 and the coefficient of the y term is even. So actually it will avoid like fractions and things like that. So I've worked that out and you get this solution here. And if you plug that into our equation for x, x equals 2 minus 4y, you can get the corresponding x values. And you see how the plus minus flips again because we've got minus 4y in that equation. Again, if you're not so comfortable with this plus or minus notation and you think like maybe it might get mixed up, just do each one individually. But if you can get competent with that plus or minus notation, it's really handy for these kinds of questions. You can keep things concise and save yourself a bit of time. So we're looking at an example like this where there's a slight twist on the question. So it's actually a little bit simpler than some of the ones we've seen prior because we've just got a simple linear equation. We've got quite a simple circle equation here. Like if I move the 9 to the other side, you'll see that's essentially a circle, isn't it? But we've got this unknown constant. And we're given this extra information. Like we're told that these simultaneous equations only have one solution. And we need to use that to find out the value of k. Right. How would we approach something like this? So it's simultaneous equations. So let's approach this as if like we're just solving simultaneously as usual. So we know what we need to do. Make that linear one explicitly in terms of x or y. So we've got x in terms of y plus this unknown constant. So I can substitute that into the other equation. So where there's an x, I'll just put y plus k. I'll expand all that out and you get this. Now, what you want to do is you want to get it into the usual quadratic form. That's what we always want to do, because this is a quadratic still. Like, y is our variable. K is just an unknown constant. Y is the variable that we're interested in. And you see, we've got a y squareds, we've got a y term, we've got constants. So let's collect those together. So we get a y squared term, we've got a y term, and then we've got a constant term equals to 0. So you can see this is still our quadratic in its usual form. It's just those coefficients a, b, and c that we normally get. The y squared, the y, and the constant term. They're just in terms of this other unknown constant k. And this is then where we invoke that piece of information where we're told that this simultaneous equations only have one solution. Now, think back like when we hear that, like when we're told like, oh, how many solutions say something has, what does that correspond to? It corresponds to the discriminant. So when the fact that if this simultaneous equations only have one solution, then the discriminant of this quadratic that we have must be 0. So that's the key step there. And so the discriminant, which is b squared minus 4ac, that must be 0. And so if we substitute in our values for a, b, and c, which are in terms of this k, and you can expand all this out and simplify, you see we get just a little equation for k that we can solve. And we get k is equal to plus or minus 3 over 2. So we can see it's when k is equal to plus or minus 3 over 2, that's when these equations will only have one solution. So very tricky one. That is very much like a top grade question. It's using a lot of skills there. So you might want to go over that a couple of times, make sure you understand that. But whenever you see something talking about, oh, this only has one solution or whatever, the discriminant is coming in somewhere there. Because the discriminant is what determines how many solutions something has, what a quadratic has. But you see this solving these simultaneous equations is kind of similar to, it's equivalent almost to solving a quadratic. Right, so that's it. That's what we've done. We've done everything we need on nonlinear equations, really. So now let's look at just final examples where the simultaneous equations that we get in these kinds of worded problems are normally very straightforward and easy. The tricky part is, how do you form them in the first place from this information? So we're looking at an example here where this guy Alex, he's investing in money in 2 accounts, account A, account B, with perhaps 2 different banks, and they're offering different return rates. One will give you 5%, per year. The other one gives you 3% return. He's invested X amount in A and Y amount in account B. Over the year, he earns a total of £220 of interest from a total of 5,000 that he invested at the start of the year. How much did he invest in each account? So if it didn't tell you what your variables are, like here it's told you your variables are X and Y, that's what we're trying to solve for. But here it's asking how much did he invest in each account. Well, okay, then we could label that ourselves, say X in account A and Y in account B. So we need to form some equations of this. And we've got 2 unknowns that we're trying to find. So straight away, that should be telling you, okay, this is a simultaneous equations problem. So we need to get 2 equations of our 2 variables, and then we could solve them. So first of all, we've got a simple one we could get is x plus y equals 5,000, because we were told that he invested a total of £5,000. So if you invested X amount in A and Y amount in B, X plus Y together must be 5,000. The second equation might be a bit trickier, which would look something like this, because he got a total return of £220. And we know account A gives you 5% and account B gets you 3%. So, okay, if he's invested X amount in account A, then he's going to get back 5% of that as interest. If he's put Y amount in account B, then he's going to get 3% of that as interest. So 5% of X, if we put that as a fraction, it's basically 5 over 100. If 3% of Y is basically 3 over 100. So if we add those 2 together, that should come to 220. And so you see there, you think it through logically, and you can work out what those 2 equations are going to be. Now it's just a matter of solving these. So first of all, we probably want to clean up that second equation a bit, like get rid of those denominators. So if we times through by 100, we can get 5x plus 3y is equal to 22,000. Then if we just solve these two, so you could do this using substitution or whatever. I chose to do elimination because I feel we've done enough substitution for today. So I times the top one through by 5. The x terms now match, so I can subtract the 2 and I get 2y equals 3,000. Y is equal to 1,500. And if y is 1,500 and we know x plus y is 5,000, x must then be 3,500. So you see, once we've got our equations, you know, compared to other stuff we've been doing on nonlinear equations now, this is very, you know, should be very straightforward. The tricky part, yeah, like I said, is getting those equations out. So there's an example of how you piece together those equations. So you just got to think, what are your x's and y's here, and what exactly is happening to them, and how do they relate to other values? Because that's why I always keep using that word relationship. That's what an equation is. It's like a relationship between different variables. Right. So one last example, which is a common one you might come across, is like an algebraic one here, where you've got not algebraic, well, it is algebraic, but geometric problem as well, because we're dealing with a rectangle shapes. Normally it will be with a simple shape like a rectangle. And we've got something like this where we've got unknowns on the sides. We need to find those out. So you might be able to spot, we can find out what the A is quite quickly because, okay, if we multiply the two perpendicular side lengths, 8 and A, it will equal the area, which is 88. So 8A is equal to 88. So A is 11. But we could use other properties of the rectangle, which is that opposite sides are equal to one another, aren't they? So we could get 2x, sorry, plus y is 11. So that's the opposite vertical sides. And then 3y minus 4x is equal to 8. So that's the horizontal sides. And so there you go. We've formed two equations of x and y that we can solve now. So what have I done here? I've multiplied through by 2 on the top equation. So I've chosen to use elimination again. Now I've got 4x and minus 4x this time. And I haven't got them perfectly lined up. Like, you don't have to have them lined up, but sometimes that can help if you're not so confident with these. How am I going to get these to eliminate? Well, I'm not going to subtract. What I'm going to instead do is I'll add. So 4x plus minus 4x, that will get them to cancel out. So see, sometimes it's not always going to be subtraction with the elimination method. Sometimes you'll add, and it depends what you're trying to cancel out. So be mindful of that. So now we're doing 2y plus 3y, which will be 5y, 22 plus 8, which will get us 30. And so therefore y is going to be 6 if we divide both sides by 5. And so finally, I've gone back to the original equation of 2x plus y is equal to 11, substituting my y equals 6, and we can always rearrange that to find x is going to be 5 over 2. So again there, so it's kind of pulling on different skills there, you know, geometry skills and area and all that. But the end goal is still the same. You know, if you've got two unknowns that we need to solve for, then we need two equations, and then we can solve those equations simultaneously. Right, so here we go. That's the end of this lesson. So today I'm leaving you with a bit of a challenge question. So there are some strange things that can happen when solving simultaneous equations. So I've got two examples here, two problems, with the first one being two linear equations, the second one being a linear and a quadratic. And you'll see both of them will come to peculiar solutions, and see if you can explain why you get those solutions. Perhaps you might want to try plotting them using some, you know, graphing calculator, or you could plot them yourself on paper and see what happens, and using that graphical interpretation we have of what simultaneous equations are and their solutions, and it should reveal why you get those peculiar solutions. So here we go. This is the end of the lesson. Here's your takeaways for today's lesson. So we've been doing so much algebra recently. We are now up to the last lesson of algebra next time, which is going to be sequences. Might not sound like it's an algebra topic, but it actually is. So we're going to be applying a lot of what we've seen so far in that lesson, and then we're done with algebra and we're going to be moving on to geometry. So I'll see you in the next lesson for our last lesson on algebra.